Hi, everyone. Mike Muller here from Rutgers University for another exciting edition of IAC 101. Thanks again for tuning in. Today, we're going to take a look at steam. Steam, like many of our other topics, will be broken up into two parts. This first video will include an intro type steam presentation discussing primarily the boiler itself. In the next video, we'll talk about distribution, end usage, and efficiency issues. So what's the big deal about steam? Why wouldn't you just use liquid water to heat or even air? Why use steam in particular? Well, as you might have guessed, it basically comes down to the energy that gets stored in the molecules as you change phase from liquid to vapor. This transitional energy has a number of different names. Enthalpy of vaporization is one you might hear regularly. And the graph shown here refers to the heat needed to complete the phase change, and we often refer to that as latent heat. So let's start off thinking about cool water at some constant pressure. We're going to heat the water up, and in doing so, we find out that it takes a certain amount of energy to heat the water up to the phase change temperature. That we would call sensible heat transfer. Then when we start to change phase, we find that the temperature stops changing. But there is a dramatic increase in internal energy on the order of about 1,000 BTUs per pound mass. This is heat transfer needed to change the water from liquid to vapor. And that's the energy storage potential that we're talking about. We can store the energy in vapor, and then we can release it by condensing that steam back to liquid water. Because the temperature doesn't change here at all, it becomes an ideal way to control temperature by controlling the pressure. So, one obvious advantage of steam is its ability to store energy. But following on to that previous point I just made, another is the fact that the boiling point, the temperature at which water changes phase, is highly a function of pressure. Here you see a plot where we've used both metric and English units, and on the bottom is the pressure in atmospheres, which is the same for both units. Now, if you're talking about Fahrenheit, you can see that at about 1 atmosphere, our boiling point is 212 degrees. But if we lower the pressure, you can boil water as you start going into a vacuum at very low temperatures. And then as you go above atmospheric and increase the pressure, you can see that you can actually increase the boiling point to some very high temperatures. This means that you can control your steam temperature by just setting the pressure. Let's say you want 450 degrees Fahrenheit. If you just keep the pressure at 40 atmospheres, then the temperature of the steam will be fixed at 450 degrees Fahrenheit. And this obviously holds true for degrees Celsius as well. As a final major advantage, it is worth mentioning the fact that steam, even before any of this storage stuff was known, has been very useful. You know, when you change water to steam in a box, you create a very high pressure, and we can use that pressure to move stuff. And this is the operational basis for the steam engine. Historically, steam engines were developed as a way to pump water out of mines. England loved their coal, and as they used up the stuff near the surface, they had to dig deeper and deeper to get it. Well, as you can imagine, this much digging would frequently put the mines below the water table, so water would continuously go into the mines and have to be pumped out. So an interesting story is that horsepower, this ubiquitous unit of power, came from having ponies or horses in the mines simply walking around in a circle to operate a pump that's pumping the water out. So when you had a steam engine to sell, you could replace the horses and therefore quantify the replacement in terms of horsepower. Now, if you look at the advantages in steam engines and steam power, it quickly developed into the area of naval warfare. If you could use an engine to power your boat instead of sails, imagine in a battle what an enormous advantage that could be. Now, this was recognized as a viable solution at the time, but there were limitations in terms of how far a ship could go on steam. So here's a picture of the USS Fulton from 1837. It's a typical ship for that time, and you can see that it had sails to get to the battle, in addition to a paddle wheel driven by a steam engine for moving around, and putting its weapons and guns into the appropriate position to do the most damage. That paddle wheel was a great target, by the way, for the enemy and was quickly moved inside the ship in subsequent designs. Now, another very important development in the US after the steam powered water transport would be steam locomotives. These locomotives started off hauling coal, but eventually we reached the point where they were hauling people, which included connecting the East to the West. Now, if you look at the picture here of an old-fashioned steam engine circa 1829, 1830, you find that this engine would increase the pressure first by using a boiler. Now, pressurizing that steam pushes the piston back and forth, which then discharges steam through the smokestack. While they could haul about as much coal as they needed to fire these boilers, what they couldn't carry enough of was water. Whatever they boiled, they put out the stack. In many cases, long trips were interrupted many times by the locomotive stopping at water towers. That slowed you down and gave the outlaws some place to lie in wait and attack you when you stopped. And finally, we should not forget that steam and its motive power have been used for 150 years now in order to make electricity. Here's a drawing of Thomas Edison's Pearl Street Station in New York City, circa 1883. You can see that they had dynamos, which we won't talk about in this lecture, but that's a way to change rotary motion into electricity, and they were powered by steam boilers. 2 floors of steam boilers, 1 floor of dynamos. So now we've talked about these 2 positives, the capacity to store a lot of energy in steam and the ability to set a particular pressure to control temperature. And so let's look at a couple of applications where these become very valuable. The first is the idea of carrying steam a very long distance. If I have a very long pipe and I put steam in at one end, and let's say that pipe is 2 miles long, okay, down that line, if we still have steam in the pipe at the same pressure, let's say 100 pounds per square inch above ambient, something like that, it's going to have the same temperature. So here I have a 2-mile long pipe where the temperature is constant. Well, you say you're going to lose some energy, obviously. And now as that energy leaves, that's going to happen by condensing some of that steam and it's going to become liquid. And all we do is replace that liquid with more steam from the source, and we continue to maintain steam in the pipe. So it'll always be at the boiling point wherever the pressure is the same. Thus, we can go for very long distances and always have the same temperature to put into our heat exchangers or other systems. Consider, for example, skyscrapers in New York City. By the way, in New York City, steam doesn't actually come from a boiler on site. You actually sign up with a large-scale external system, usually utility, that delivers steam into your building. Now you can go up 100 floors to the top of your skyscraper, and the temperature of the steam at 100 floors up will be the same as the temperature of the steam when it was first brought in from the underground steam pipes. If we think about the Empire State Building as a particular example, you'll find 7,000 radiators there. Yet if we look at the steam traveling from the bottom to the top, the pressure of the steam only drops a few pounds per square inch. So the temperature of the steam is going to be just about the same at the top of the skyscraper as it is at the bottom. Let's look at another application where the use of constant temperature of steam helps you in chemistry, or in this case, more specifically, cooking. Here we have the picture of a heated cooking vessel where a constant temperature is desired. So what we do is simply put steam at a particular pressure to fill a jacket surrounding whatever it is you're trying to heat. As heating occurs and energy leaves the steam, yes, some condensation is taken out and replaced with steam. And then you know what the temperature is and that it is in fact constant. Now, if you're cooking spaghetti, this might not be that important. But if you're talking about chemical reactors where you're trying to control the chemistry very accurately, this is an ideal way to maintain constant temperature. So before going into the boiler itself, let's look at the various parts that we're going to cover as we move forward in our discussion of steam. Here's a nice picture of the overall parts of a steam heating system. We'll start today on the generation side with the boiler, water treatment of the water in the boiler, and feed pumps into the boiler to bring water in to boil. It also involves all the combustion processes that would take place and waste heat recovery through an economizer and the preheating of combustion air. Now, know that after combustion, the products of combustion have to go out of a stack and you have to throw them out, usually through the roof, and you get nothing of use from those hot gases. So it's something we want to minimize as much as possible. All of those processes fall under the heading of the generation of steam. Now you have steam that's ready to go into your plant. This will require a distribution system that's going to include piping, valves, pressure reduction valves, a lot of insulation issues, and things called steam traps. When the steam loses energy, so some of it becomes liquid, we have to trap that liquid back out of the piping system, out of the distribution system, and return it to the boiler so you don't lose a lot of the water that you already paid to both heat up and clean. Now, the end uses of steam, meaning applications, are quite similar to those we have discussed in our process heating videos, and we've already talked a lot about them. But there's still some issues associated with the end use of steam. Finally, it's important to talk about the recovery, where the water that condenses goes through these steam traps and into a condensate return tank and a deaerator, an important device that we're going to have to talk about, and then back to the boiler. So recovery is important. So let me start with a few comments about boilers. One important thing to keep in mind is operating boilers safely. If you look here, you can see that there's a sign in this picture. It's a little askew that says boiler room, and behind it are the remains of an exploded boiler. When we're talking about boiler operation, it's necessary to recognize that there are very high safety concerns when you have steam at high pressure. First of all, the boilers themselves are large and heavy. And secondly, we want pressures to be very high. This could be 100, 200 pounds per square inch. But if you have a very large boiler and you do that hundreds of pounds per square inch times a lot of square feet, that's a tremendous amount of energy. And sometimes that equals boom. Okay. In the early days, boiler explosions were very frequent. And so standards need to be set for pressure vessels and the welds that put them together and those kind of things. Interestingly, this was the driving force behind the formation of the American Society of Mechanical Engineers. I'm a mechanical engineer, so that's my professional society, and they are still, as of today, making big bucks off of their codes for pressure vessels and welding. There's another group called the National Board of Boiler and Pressure Vessel Inspectors, referred to usually as the board, and they do the same thing. That is trying to ensure that boilers are safe and that they meet standards. Now you might think, okay, that's old base stuff. But I was in a plant not too many years ago, which had a boiler that we assessed and tried to consider ways to improve its performance. Then about a year later, the boiler exploded, so I'm glad I wasn't there on that day. They probably would have blamed my team somehow. Now, when we're talking about boilers, one of the things to realize again is that the term boiler will be used for devices that don't even boil water. Sometimes it's just really a heater. And people might say, oh, that's the boiler. And you might be stunned actually that no boiling takes place. Another phrase you hear is something called packaged boilers. Oh, we have a packaged boiler. This is a vestigial term. In the old days, you used to buy boilers in pieces, the combustors, the heat exchangers, that sort of stuff, and put them together. Today, if you buy a boiler, it all comes in one package, and sometimes people still refer to that as a packaged boiler. Let's move on to some other useful definitions: design pressure and operating pressure. And you need to understand both of these, but they're different. Design pressure is really the maximum pressure and has to do with how you design the thickness of the walls and piping and things like that. As we design the boiler, we will add pressure release valves that are set to go off at or below this design pressure for safety reasons. Then somewhat lower than that should be the operating pressure, which is what you want to operate at. But the closer it is to that design pressure, the closer you're going to be to what we refer to as nuisance trips. Because if you get a little high, these pressure valves open and the boiler often will shut down. You might, oh, the boiler cut out because the pressure got too high. And you go, well, listen, that really shouldn't have happened because the operating pressure should be well below the design pressure. Now, boilers themselves come in two major flavors: fire in tube and water in tube boilers. The definitions here are pretty self-explanatory, but a fire in tube boiler normally uses fossil fuels. We'll talk about electric boilers at the end of this. And it's essentially a big tank of water with hot tubes inside, as can be seen in the figure here. When it reaches steady state in terms of operation, there is water up to some level, and then some steam above it, which gravity forces to the top of the tank and will be available to be tapped out the top. A burner is usually located near the bottom of the boiler and creates a huge flame which flows into a large cavity. And the path of hot gases passes then through the water a few more times and then exits out the top. Now remember, whenever there's an open flame, there'll be radiation heat transfer as well as convective and conductive heat transfer. So as a designer, you want a lot of surfaces to see the flame more effective. So you normally surround the flame with as much water as you can, especially underneath. This wasn't always the case. In the old days, the bottom of the boiler seeing the flame was not water, but refractory, something like bricks. Not only was this inefficient, but the bottom could get so hot it could burn through the hull of ships, which would then pretty obviously result in a disastrous outcome. That's why the design where the big flame is surrounded by water is called a Scotch marine boiler, after the Scottish shipyards that built boilers for marine vessels for the British Navy. On those subsequent passes, the hot gases continue to heat the water through convective and conductive heat transfer. Now, fire and tube boilers have the benefit of containing a huge tank of water. So once you get it heated up, it easily handles changes in load. But because it's a big tank of water, you really can't have too high pressures. So you would expect to see this type of boiler at the low end range of boiler pressures, typically operating under 300 psi. Now you do notice I talk psi a lot because this is a US program we're talking about, but you could have atmospheres or kilopascals or whatever you wanted if you're looking at metric system boilers. One thing that's changed over my lifetime arises from the fact that these fire and tube boilers are subject to hardly any economies of scale, meaning you don't get more efficiency if you get a bigger boiler. And so you end up seeing the need for large boilers being replaced by what are called gangs of smaller boilers. In this picture, you can see 4 equally sized boilers that are serving what would have historically been one much bigger boiler. This configuration provides some advantages. One, you can match the load by turning individual boilers on and off, which is very efficient. And we have what we call fault tolerance. If one goes out for whatever reason, needs repair, maintenance, etc., you can go ahead and just run the other ones. Now, if we want to get bigger, especially in pressure, we're going to have to switch to the type of boiler called a water in tube boiler. What we have here are combustion gases in space, and then there are water in tubes across which those hot combustions pass through. These are often used for higher pressures and therefore higher temperatures. These boilers are characterized by drums, which are places where you can have liquid and vapor separate. So let's go ahead and take a look at one here. This is an industrial sized boiler, and what you're seeing here is a lot of pipes which contain water that is intended to boil. The burners are on the right, and there's essentially an enormous furnace area inside, surrounded on all sides by walls of pipes. Let's focus on the 2 cylinders on the left, one on top of the other. The top cylinder is called the steam drum, and this is the place where we separate water from steam. Steam goes out the top and often back toward the flame to superheat, and then out to wherever you need high pressure, high temperature steam. The liquid in the steam drums flows downward, again seeing the flame to heat more and the change phase itself. The lower drum, or what's referred to as the mud drum, is where liquid and water gathers and any solids can separate out. Recognizing that there's going to be a little junk in the water or coming from the pipes, you can gather those solids in the bottom and periodically get rid of them. Up to now, we've been talking about steam that is saturated and follows that curve to the boiling point. For example, if we had an atmospheric pressure boiler, you would have steam at 212 degrees Fahrenheit or 100 degrees Celsius. But you can always take that steam and put it through more processes to get it hotter. Now, you're likely to see a lot of water and tube boilers, and you're always going to see them in this two drum configuration. So when you walk into a plant and you go around looking at boilers, you can tell without even asking whether it's a water and tube or a fire and tube boiler. Both of these boiler types that we've been talking about are typically fossil fueled boilers, but there are a few reasons in a plant where you might want to use an electrically heated boiler. We find that this is more likely to happen these days with a modern push for decarbonization. The Department of Energy has a series of certain targets for industrial plants to get rid of all of their carbon fuels. If you can't use carbon fuels, then you'll have to use electricity, so we should see more of them in the future. However, we do see them today for specific applications. These electrically heated boilers tend to take the place of smaller boilers, and you can spot them right away because they don't have a stack. They don't have to get rid of any combustion products. One application is to get around the need to have a full-time boiler operator. If you have less than 15 pounds per square inch of gauge pressure, normally you don't need to have an operator. If you need a lot of steam on, let's say, 6 or 7 production lines, what I've seen is plant owners do is to put a small electric boiler at each production line to provide the needed steam. Because there is no stack needed, you can just bring them in, plug them in, and run them. So you do have an upper limit of pressure and therefore temperature. Let's finish up by talking a little bit about the water that's in the boilers and its quality, which, because you're going to boil it, has to be extremely good. Depending on your source of water, quality issues could be a big problem. Since it's from the ground, there's often a lot of associated chemical costs to treat it. One of the things we normally do is discuss with a boiler operator the various steps that are being taken to make sure the water is as clean as possible. This can include chemical treatment and the cost of chemicals, dissolved gas removal, and this can be done with a de-aerator, which we'll talk about when we get to recovery. And there are also filters, strainers, anything that you can get rid of chunks that are in there. And you can get into some very fine filtering processes such as reverse osmosis. The goal is to remove both dissolved and suspended solids and gases. Even when they might not seem to be hurting your system now, if you don't get rid of them, they eventually will. One thing we've learned, however, if a plant is not experiencing any water quality issues, they're going to be very reluctant to consider any changes. And recognize that water treatment is a continuing issue because you're going to lose steam and need to replace it with makeup water. Sometimes the process in the plant uses up steam as well. Like think of a corrugated box plant where steam is used to humidify the paper in the corrugator, the thing that makes the wave-shaped paper. In some chemical processes, no steam is actually returned to the boiler at all. Then, of course, there's always the potential of leaks. Ultimately, where you're using up steam, either by leaks or processes, which started as innately pure, certain impurities within the boiler itself will start to increase in percentage. We can track that percentage by looking at the concentration of dissolved and suspended solids in the water, normally with some instrumentation that simply looks at the electrical properties of water. In order to get rid of that now dirtier water, boilers will need to drain some of that liquid periodically or continuously. Okay, in both cases, it's referred to as blowdown. Sometimes it's done in a periodic fashion, let's say blowing down the boiler every Sunday, for example, or sometimes continuously where there is flow coming out of the bottom of the boiler intended to remove those impurities. And this is nasty stuff, so sometimes it's pretty hard to control accurately because valves will foul and wear. Periodic systems, like the one you would open just on Sunday, can often remain open just because of leaks, and continuous systems can be discharging the wrong amount, either too much or not high enough. If you're not discharging enough, then the amount of dissolved solids will continue to grow. If you're discharging too much, then you're throwing out hot water. So now you have to replace the water again and heat it up so it becomes an efficiency play. We have looked occasionally at potential solutions to recover heat from the blowdown process, such as preheating the makeup water, which comes in where there are large amounts of blowdown. Keep in mind, however, that the reason we started talking about water treatment was because pursuing better water treatment reduces the amount of blowdown you have to do. Now that we have steam being made in our boiler, we'll need to take a look at how it gets distributed throughout the plant and then how it gets used and recovered. We'll be holding these topics for part 2 of our discussion on industrial steam systems. Thanks for listening. Hopefully you've learned a little bit, and we will be seeing you in the next episode. Farewell.